So, just like in axial, we started off with some kinematic descriptions and had that the strain shows us the derivative of displacement field with respect to x. Now, analogous to that, origin, we showed that shear strain gamma is equal to d dx. That's the derivative of the angle of twist with respect to x times the rho. Remember, it had that additional issue that it's proportional to the radial distance. Now, in the axial case, we then wanted to get the elongation. And we got that by multiplying d by dx. Integrate both sides, get u on the right-hand side, and we substitute in for the strain in terms of the parameters we know a little better, the internal forces, geometry. So we know that the strain is the stress divided by Young's modulus, right? It's law. And we know that the stress is the force of the area. So we'll integrate both sides. Displacement, that's the integral of e dx, so let's call it right? So that gives you the elongation in general as an integral, and then we also talked about situations where A, E are constant down the length, which is pretty typical, and that gives us that elongation, which displacement L is E L. Right? So we do the same thing with torsion. Think about what's analogous. The strains, the measures of the deformation in axial, it's the displacement in torsion and angular twist. So we have this little rho factor as well. All right, so we're trying to find the angle of twist, right? For those who forget, that's the disk's twist relative to how much this front disc rotates relative to the back disc as it moves downhill. Okay, so dP is going to equal gamma over rho dx. Right? Similar to what we did here. We're going to integrate both sides. Now, in this case, gamma, the shear strain, is going to equal the shear stress over G, even here. And the shear stress, remember, is T rho J. J is that second polar area moment, right? So this now becomes T rho J G. And you can see it's pretty analogous. You have the area corresponds to J. Young's modulus corresponds to modulus rigidity or shear modulus. The internal reaction force is P for axial, and then that corresponds to the internal reaction torque, T, for the torsion, and we have this additional rho. So take that, put that in here. Now I have integral P equal to putting in this for the shear strain. You can see that the rho's, the radial distances cancel out, and this gives me T on J dx. Right? So it's the integral d of x equations are analogous, right? Again, this is the general equation that tells you how much a disk at some distance x from one end rotates. You have to perform this integral, just like we have to perform the integral to figure out the displacement along the axial direction of the axial case. But very often we have, again, a situation where the internal reaction torque, the area factor, the geometric factor J, and then G are all constant. If that's the case, they can all come out of the integral, and then we're just left with P at L, that's the total angular twist, T, L, J, G. So that's the angular twist. And, again, if you memorize this equation, you can see it's the same equation. Instead of P, we have the torque, L is still the length, J is the geometric factor for torsion, and then since we're dealing with shears, we have G, the modulus of rigidity, as opposed to Young's modulus. Okay? So this will tell me if I have a section here that undergoes, has constant cross-sectional area, and they have the same material, so G is constant, J is constant, and if we put torques at the end, that means the internal reaction torque is constant all along the section, no change. That means we can figure out the angular twist. The front hand moves relative to my back hand, and that is TL on G. Okay? That's it. Pretty easy. I think in general for a lot of this stuff, you see the same with bending. If you keep straight the analogies with axial, it's